All right. It's a pleasure to welcome our next speaker this morning. It's Armin Weiss from Stuttgart, and he is going to tell us something about parallel computation for word problems in groups, Baumslag-Solitar groups, and related something. Armin, please.
Yeah, thanks a lot for inviting me. So yes, it's about parallel complexity of Baumslag-Solitar groups and related. So Baumslag-Solitar groups, most of you might know, it's a group generated by these two generators, A and T conjugates A to the P to A to the Q. So it can be seen as an H&N extension of an infinite cyclic group with infinite cyclic associated subgroup. And as such, it can be generalized to a fundamental group of a finite graph of groups with infinite cyclic vertex and edge groups. And that's a GBS group. Yeah, so in the following, I will call it GBS groups. And so I won't be talking a lot about GBS groups, but everything which holds for Baumslag-Solitar groups in this talk also holds for GBS groups. So I just want to mention them. Then I have another relative of Baumslag-Solitar groups, and that's the Baumslag group. So the Baumslag group, it's an H&N extension of the Baumslag-Solitar group, again with an infinite cyclic associated subgroup. And so we take this extra letter B and say that B conjugates A to T. Yeah, so we get this extra relation, B conjugates A to T. And yes, so now we can see that P is actually just an abbreviation for BAB inverse. And so we can see that actually just A and B suffice to generate the group, and it's a one-related group. Okay, so these are the three main classes of groups I will be looking at. And now the verb problem should be also known. So we have a group generated by a finite set sigma, and I assume that we always have all the inverses, but that's not really necessary all the time, but it makes everything simpler. And well, I always write a bar instead of a inverse. Just it looks nicer, and we can distinguish whether it's a different letter or just we mean the inverse in the group. Now the word problem is I give you a word and I want you to decide whether this word is actually represents the identity of the group. Yeah, or it also can be seen, I give you two words and I want to know whether the two words represent the same component. A related or variant of this question is the compressed word problem. Here I give the input word in a compressed form as a straight line program, or also can be seen as a circuit over the group. And of course, in terms of decidability, these two things are the same, because if I have a compressed word, I can uncompress it and solve the word problem. But in terms of complexity, the two things might be different. Now I want to focus on parallel complexity of the word problem. So why should we study parallel complexity? So the first reason is with parallel complexity, we can study complexity within polynomial time or even within linear time. If you have a sequential algorithm, you cannot do anything mini.
Armin? Might have a connection problem. Hello?
Is there a question?
I think we lost you for a second, or maybe just your audio disappeared. So now you're back.
And now I'm back. Okay. Should I repeat something?
Maybe the last couple of sentences, yes.
Okay, yeah. So we can study parallel complexity to study problems within polynomial time. And we can, it's also of practical relevance, parallel complexity, because many like GPUs or even CPUs now use massive parallelism. And also we can study it because it aligns nicely with group theory. I will say a little bit in a few moments. Now, there's several models of parallel computation. The first one is a parallel random access machine. So it's essentially a theoretical model for a GPU. Then the second thing is circuit complexity. That can be thought more like a theoretical model for actual hardware circuits. So not on a level of transistors, but on a level on OR and AND gates. Or we can also use log space. So log space intrinsically is like sequential algorithm, but we restrict the space. But we know if we have a log space algorithm, it also means that we lie in some small parallel complexity class. And the easiest of these parallel complexity classes is AC0. So we have circuits. That means for every different input size, we need a different circuit. So we always talk about families of circuit. And AC0 means we bound the size of the families by some polynomial, and we bound the depth by some constant. Yeah? So the 0 here, it stands for constant depth. And then we allow and, or, and not gates. So just the use of Boolean gates. Yeah, and now, of course, constant depth only makes sense if all and or gates have arbitrary many inputs. Otherwise, we cannot do a lot. Yeah, so we can have arbitrary many inputs. Okay, now let's look at some word problems in these circuit classes. Yeah, so in AC0 can also be seen as we use first order formulas with quantification over positions in the word. So that's the same as AC0. And there are not many word problems of groups. So actually, they are just the cyclic groups with one generator. Because if we have a cyclic group with one generator, whether the word is one in the group depends only on the length of the word and nothing like the word itself. Yeah. So basically in AC0, we cannot do any word problems of groups. The next class is ACC0. In ACC0, we also allow oracle gates for finite cyclic groups. Yes, but for each language, we have to fix to one finite cyclic group. We cannot use like all finite cyclic groups because then we also could do the infinite cyclic groups. And now in this class ACC0, we actually cannot do just only the finite cyclic groups or finite abelian groups, but we can already do all finite solvable groups. Then as a next step, of course, we could say, let's take infinite cyclic group, and then we actually get this class TC0. And TC0 is also like interesting because if you think what is a neural network, it's like these neurons, they sum up their inputs and output one if the sum is large enough. So this is kind of, well, we are using the addition in the infinite group of the integers. Yeah, I mean, there are some details in the translation, so it's not straightforward that we can say every neural network is a TC0 circuit, but it's kind of a reasonable theoretical model for them. So also a reason why it should be interesting. Okay, now what can we do in ACC0 with integers as oracle? So we can do all linear solvable groups, the word problems, and actually they are complete for this class as soon as they are infinite. So in particular, of course, we can solve the word problem of the integers itself. We can also solve the word problem of those Baumslag-Solitar groups BS1Q, which are solvable linear, and we can do all polycyclic groups. And the class of the groups with word problem in TC0 is closed under wave products. Now the next step is, well, until TC0, we only get word problems of solvable groups. Now, if we it's also like an open question whether there is a non-solvable group with word problem in TC0. Now, if we add like the first non-solvable group we can think of, the alternating group of order 60, then we get this class NC1. And actually, in this class, we can do word problems of all finite non-solvable groups. So in total, we can do all finite groups. Because one can show that also the word problem of the integers is in NC1. Okay, can you still hear me? It's somehow it says the internet is, yeah, okay. Good. And also all regular languages are in this class. Yeah, and so actually this class is also closed under finite extensions. Then we can go a bit further. Like the next group you might imagine after finite non-solvable groups might be the free group. And so in the free, for AC0 with oracle gates for the free group, we don't have like a nice genuine circuit description. So we just have this AC0 and use oracle gates. But in this class, we can do really a lot already. So we can do all virtually free groups. We can all the Baumslag-Solitar groups and GBS groups. We can do all the right angle arcing groups. So also we can do their subgroups. And since it's closed under finite extensions, all these virtually special groups. And the class is closed under free products, or more generally, even graph products. Now, there is a famous result by Lichten and Sargstein that all linear groups are in log space. So that means linear groups are in log space. That also means that the word problem of the free group is in log space because it's linear. Yeah. So we have that the next step in this hierarchy is like log space, and there we can solve linear groups and the group orchard and others. But here in this case, we don't know whether the word problems of these groups are actually complete for log space or not. Yeah. So in the AC0 of F2, we always, in all those examples here, we had free subgroups, so they were complete for AC0 of F2. And yes, so if we want a complete problem for log space, within group theory, we can think about the uniform word problem for finite permutation groups. Yeah, so we give you a bunch of permutations over some n elements, and I want to compute the product. So that's a log space complete. Then after log space, the classes are getting more and more powerful. And in AC1, so AC1 is now like AC0, but the 1 stands for logarithmic depth. So yeah, exactly the same Boolean gates, but now logarithmic depth. And then we can do Thompson groups and hyperbolic groups. Yeah, so these groups are not complete for this class AC1. So there are also some classes between AC1 and log space where these groups are known to lie in, but yeah, too many classes are, yeah, not good, I think. So then the next step is we can do the same game as before and add oracle gates for other groups. So we can do AC1 with integer oracle gates. And then we can do the Baumslag group. So B, P, PQ. Yeah, so only the case where P divides this PQ. We don't know about the other case. And then, well, this is all in the parallel hierarchy. So this is all up to TZ1. There are still many other parallel classes, but I don't know any nice groups lying in there. What problem? But then, like, we also have the larger classes. P for polynomial time. And there we know that the compressed word problem for free groups is complete. And this means we don't believe that there's a parallel algorithm. Because every polynomial time problem can be reduced to it. And it's widely believed that polynomial time is not equal to the parallel hierarchy. And if you go even further, we can go to polynomial space. And there, the compressed word problem for the Grigorchuk group or Thompson's groups become complete. Okay, so that's a rough overview over all those circuit classes. And now I want to give some small details how to show this Baumslag-Solitar group result and Baumslag group results. So the Baumslag-Solitar groups, if we consider those solvable Baumslag-Solitar groups, we have this matrix representation. And Robinson already used it in 1993 to show that the word problem is TZ1 complete, TZ0 complete. Yeah. Okay, if P and Q are not one, then we have a free subgroup. For example, this free subgroup in our Baumslag-Solitar group. So we cannot expect to be it in TZ0 because it's actually NC1 hard. But we still know, as I said before, that we can solve it in this class AC0 with F2 oracle gates. So in particular, we can solve it in log space. Okay, so next, I want to give some details on that. So we know that the Baumslag-Solitar group is this H&N extension. So this gives us a natural algorithm to solve the word problem, namely by Britten reductions. So if we have a word written over those generators, then we know it's in this subgroup generated by A, if and only if we can apply rules of this form, T A to the something, T inverse, or T inverse A to the something, T goes to A to the something. Yeah, and here depends, K is either divisible by P or by Q. We can do the reduction. And now we can store the exponents of our letters in binary notation, and then we can solve this word problem in polynomial time. Yeah, we just apply the Britten reductions until we are done. But of course, that's not a parallel algorithm. We have many steps, one after each other. So for a parallel algorithm, we can combine two main ingredients. So one is the word problem of the Baumslag-Solitar, of the solvable Baumslag-Solitar groups, yeah, and the other one is the word problem of the free group. Yeah, so at least if T divides Q, then we always have a nice solvable Baumslag-Solitar quotient, and we can compute in that way. So now, how do we do that? So we look at this picture. And well, what we observe is, first of all, if, so in this topography, if the word is 1 in the Baumslag-Solitar group, of course, we might end at the 0 level. Otherwise, we already know that in this infinite cyclic quotient, it's not 1, and so it's certainly not in the Baumslag-Solitar group. And what we do now is we want to reduce this word problem of the Baumslag-Solitar group to the free group. And we do it by assigning colors to each letter T. And we assign different colors to letters T which cannot cancel. So if you look at this T, blue T and red T inverse, there's a single A in between. So that means they cannot cancel. Yeah, because if they were like two A's, A square, then we could apply the relation T A square, T inverse goes to A cube. But here we cannot apply any relation. We can apply a relation to this T inverse A cube T, yeah, because that's equal to A square. And so we also see that this thing here potentially can cancel. So the two blue T's. But certainly the green T cannot cancel with the blue T, yeah, because it's already on a different level of this topography. Yeah, but the green T's might cancel with each other, and so we have this. And well, then we define a new word, W tilde, and that's just the T's with the different colors. So it's a word in the free group with T's of different colors, and that's the word problem of the free group. Now, how do we assign the colors? So we assign colors, we test the subgroup membership in this quotient. So this is always a quotient of the Baumslag-Solitar group TQ. Yeah, so if P divides Q, then this is exactly the solvable Baumslag-Solitar group. Otherwise, it's just some matrix group. And we just check membership for this subgroup. Yeah, so membership for this subgroup or for 1Q. Yeah, so we check some factor. So like if we check this blue T's, we check this red factor, whether it's in the respective subgroup. And if it is, then the two T's get the same color, otherwise they don't. And yeah, so then of course one has to check that this is actually, yeah, it's correct what we are doing. And of course, also we need to know how to compute it. But to compute it, it's basically solving the word problem. Yeah? So the subgroup membership problem is a bit more complicated in the solvable Baumslag-Solitar than in the solvable Baumslag-Solitar group, but it's not much more than the word problem. Yeah, and then, well, what we take some word and assign those colors. And what we prove is that the word is 1 in the Baumslag-Solitar group if and only if the resulting word W tilde is 1 in the free group, and also W is 1 in this solvable quotient. Yeah, and in this solvable quotient, we can compute in PC0. And this here, it can be solved as a word problem of the free group. And that way, we can solve the word problem of the Baumslag-Solitar group and reduce it to the free group. And actually, we can do all computation of written reduced words when reduced to the free. Okay, so much to the Baumslag-Solitar group. Now I want to say something about the Baumslag group. So originally it was defined the Baumslag group 1, 2. So we have these two relators. And as I said, it's a one relator group because T can be seen as an abbreviation for a B inverse. And interestingly, all finite quotients are cyclic. Yeah, so that's a title of the original paper. And it's known that the gain function is tower of log n. So a tower function is 2 to the 2 to the 2, and this log n times. And that was also a reason why the group was considered as a candidate for a group with a difficult word. Now we consider the slightly more general Baumslag groups. There we also allow here these exponents a to the p, and here we allow a to the pq. Yeah, but now here this one exponent divides the other exponent. That's important. Yeah, and so we have the h. We can write it as an h and n extension of this Baumslag-Solitar group. Now, how to solve the word problem? Well, we know that by Magnus' theorem, it's decidable. And actually, well, we apply the standard HNN algorithm using Britton reductions. So Britton reductions say if we have some b, a to the k b inverse, we can rewrite it to pk, t to the k, and likewise for b, p to the k b inverse. And we can also apply the Britton reductions within the Baumslag-Solitar group. Now, this approach has one problem. So here I define the power function. It's just 2 to the 2 to the 2 to the k. And yes, so I want to show the problem here in this one G12. Yeah, but in GP, PQ, it works exactly the same. So we define by recursively words by this formula. And I claim that WK is equal to T to the power of K. So this very, very, very long word in the group. Yeah, and when we apply Britton reductions, actually we would rewrite WK to T to the power of K, and that would show that this approach for solving the word problem is really, really slow or bad. Okay, so to show that this is true, it's a really easy induction. We just apply the definition and induction hypotheses, and then we do the Britton reductions, and that gives T to the power of K plus 1. The thing is, the words WK, they only have length like 2 to the K. So like if we start with a word of length n, we get something like tower of log n. So if length of WK is n, then this is tower of log n. So that's huge. So we need an idea. And for this, some clever guys came up with the notion of using power circuits. So a power circuit is a directed acyclic graph with labeled edges. So we label edges with plus minus 1. So if we consider power circuits with base q, we can also add some digits on them, but I explain them just for 2 because it's easier. And each node has an evaluation. And we say the evaluation is just the evaluation of 2 to this lambda of p. And we call lambda of p the successor marking. And it's just we take a sum over all outgoing edges and the evaluation of the successor node. Now, since this is a directed acyclic graph, this recursive definition is actually well-defined. And so we see that this one node, it doesn't have any outgoing edges. So we get the empty sum here and the empty sum. So it's 2 to the 0, which is 1. And here 2 has one outgoing edge to 1. So we get 2 to the 1. So it's 2. Yeah, so we can compute the balance. And now if you want to represent some numbers which are not powers of 2, we just add signs to different vertices and we call this markings. And we can also represent numbers which are not a power of 2. Yeah, so for example, 2022 is this marking. Now we can use, yes. Using this, we can, of course, represent very huge numbers. Yeah, we just do a chain of many, many nodes, and we can represent the tower function. So it gets huge. So we can represent, with this, we can represent all the huge exponents appearing in the solution of the word problem for the Baumslag group. So, but we also need to compute with power circuits. Otherwise, it's useless to just represent huge numbers. And one thing we have to do is, well, we have to do this calculation if Kp and Kpq to the L are integers. And now let's say for the moment Kp is equal 1, then this means Q to the L should be an integer. And that's the case if and only if L is non-negative. And well, so we need to solve the power circuit comparison problem. Yeah, so I gave 2 markings and I want to know whether one is less than the other. Yeah, so actually 1 could be 0. So we just want to know whether 1 is less than 0. And the good thing is that we can solve this in polynomial time. The really bad thing is that this problem is P-complete. So P-complete means we don't believe it's doable in parallel. So that means if we just follow this algorithm, the Britton reduction, and use the power circuit compression, we have to solve this P-complete problem, and we are stuck. We cannot do it in parallel. Now, the good thing is, of course, I wouldn't present this here if we were stuck with that. We can circumvent it. We can not use general power circuits, but so-called reduced power circuits all the way through. We always keep these power circuits reduced. And a power circuit is reduced if every vertex has a unique value, and the vertices are sorted by their values, and the markings are compact. So that allows for some unique representation of integers. And then we can show the following lemma. So it's all things are doable in TZ0. So we can compare two markings in TZ0, and we can do addition in TZ0, and we can do this operation, K times Q to the L. And actually, we can do even a bit more. We can do iterated addition. So we can take an arbitrary number of markings and add them together all in one TZ0 step. And we also can do many of these operations in parallel. So this is really important because usually if we use binary numbers, you can compute 3 plus 5 and 10 plus 11 completely independently. They don't have to do anything. But now if these 3 and 5 and 10 and 11 are like pointers to the same power circuit, then they are not independent anymore. Yeah, so we really have to do something to still can do them independently in parallel. And then, so we can use this lemma to show that also in TZ0, we can take two Britton reduced words for some group elements in the Baumslag group and compute a Britton reduced word for their product. Yeah, so we start with UV being Britton reduced and reproduce something W to be Britton reduced. And then we can use this in a tree-shaped manner. We start with single letters and Britton reduce their product. Yeah, we do this all independently in parallel. Yeah, so we have many more of them. And then we take these length 2 Britton reduced word and Britton reduce them, and so on. So we get a tree of logarithmic depth, and each of the steps can be done in TZ0. So the whole thing is in TZ1. Yeah, and that's how to solve the word problem of the Baumslag group in TZ1. Yeah, so yes. So the general case PQ is still a bit work in progress, but it's like almost. Okay, but there are, of course, a few open questions. What if P does not divide Q here in this case? Then we really don't know anything. And maybe a very bold question, but yeah, are all word problems of one related groups actually reducible to the free group? We have some examples like the free group, the Baumslag-Solitar groups, all the virtually free one related groups, and some other one related groups. They are actually in this class, but we even don't know for the Baumslag groups. Yeah, and there are many other one related groups. And of course, we can also ask the same thing for hyperbolic groups or the Gregorccio groups, which are already quite low in the parallel complexity hierarchy, but still we don't know whether they are reducible to the free group. Okay, that's it. So thank you very much. And yeah.
Okay, thank you. Thank you, Armin. All right, so we have a little time for 1 or 2 quick questions to the speaker. So if somebody has a question, please unmute yourself and ask.
Yes, Markus?
Yes, so the compressed word problem for the Baumslag group, is this still open, or do you have some results?
I have no idea about it. Yeah, I think you did something about this power word problem for the solvable Baumslag-Solitar groups. But that's all I know. Yes. I don't know anything else.
Okay. So P space.
I mean, it's in P space. It's in P space because the word problem is in log space. But
yeah.
I don't have any, well, it's P hard because we have the free groups.
Free group, yeah. Mm-hmm.
But otherwise, I don't know anything.
Okay.
So I had a question. So these questions that you have on this last slide, in particular about hyperbolic groups, what's your guess? So about the parallel complexity class, are they all really in this AC0 F2? Or do you think that there may be something that is not?
I think it's really, these are difficult questions. I think these are the first one might be not so difficult. I'm not sure.
I understand that they're difficult, but what I mean is what might be true, so
it's hard to guess. It's really hard to guess.
Okay, all right. You're refusing to commit.
Yeah. So if the classes, if AC0FF2 is equal to log space or something, I would guess they are in the class, but I would rather assume yeah, I don't know. Yes.
Okay. All right. Okay. Thank you. All right. Let us thank the speaker again. Thank you, Armin. Thank you. So
yeah, thank you.
Stop the recording. So